You know, when you use a really slick app on your phone or a website that just works perfectly, have you ever stopped to think about how it was made? It's definitely not magic. Long before anyone writes a single line of code, there's this incredibly important creative process called software design. It's the architectural plan that turns a vague idea into a solid blueprint. So, how does that actually work? Let's get into it. All right, here's our game plan. We're going to start with a blueprint, then figure out what the software actually needs to do. We'll look at picking the right roadmap, learn the special language of design, see how to build a digital skyscraper, and then finally wrap up with why all this planning really matters. So, let's start at square one. The absolute first rule of making great software is that it starts with great planning, not just hammering out code. This is our blueprinting phase. It's a tempting question, isn't it? Why not just roll up our sleeves and start building? Well, imagine a construction crew showing up to a building site with just a huge pile of bricks and that's it. No plans, no instructions. It would be total chaos, right? It's a recipe for disaster. And that's really the core idea here. A software design is the architect's blueprint for a digital building. It maps out everything, from the foundation all the way up to the little details. It makes sure that what you end up building is strong, useful, and is actually what the user wanted in the first place. Without that blueprint, you're just flying blind. Okay, so we're on board with planning. The very first question we have to answer is, what does this thing actually need to do? We have to define its purpose, specifically from the perspective of the person who's going to use it. The main tool we use for this is called a use case. Now, I know that sounds a little technical, but it's actually super simple. A use case is just a story. It describes how someone, who we call an actor, interacts with the system to get something done. That actor could be a person, or it could even be another computer system. It's all about capturing goals. Let's make this real with an example we all know, an ATM. A classic use case is withdraw funds. The customer is the actor, the goal, get cash. And the steps just lay out that back and forth conversation. By writing out these simple little stories for everything the software needs to do, we create a crystal clear list of what we have to build. Okay, so we know what we need to build. Now we need a plan for how we're going to build it. This is where software lifecycle models come into play. You can think of them as different roadmaps for the entire construction project. Now, there are a bunch of different models, but let's look at two that show totally different philosophies. On one hand, you've got the classic waterfall model. It's very rigid, very linear. You finish one entire phase, like gathering all the requirements, before you can even think about starting the next one. On the other hand, you have something like the spiral model, which is way more flexible. It works in cycles or little loops, where you're constantly analyzing risks and building the product out piece by piece. But that rigidity of the waterfall model, it created a huge problem. Because you don't actually test anything until the very end, you could spend a whole year building something based on a wrong idea you had on day one. And finding that mistake a year down the road, oof, that's incredibly expensive and frustrating. And that's exactly why newer, more flexible methods were invented. You know, every architect needs a way to draw their blueprints, right? A shared language of symbols and diagrams so everyone's on the same page. While in the software world, that language is called UML, and it's built on a few really key ideas. UML is pretty much the industry standard way to draw software blueprints. Before it came along, it was kind of like the Wild West. Every team had its own funky way of drawing diagrams, which made working together a total nightmare. UML gives everyone a universal set of tools, so any engineer, anywhere, can look at a design and understand what's going on. Two of the most basic concepts in modern design are the class and the object. Think of it this way. A class is the template. It's the blueprint for a car in general. It defines that a car has wheels, an engine, car things. An object, on the other hand, is a real specific thing made from that template. Not just any car, but John's specific red car. All software is basically built by designing these classes and then creating objects that talk to each other. This leads to a really powerful idea called information hiding. Let's go back to your car for a second. To drive it, you don't need to be a mechanic, right? You just use the steering wheel, the pedals, the simple interface. Information hiding is the exact same concept for software. It tucks away all the complex, messy inner workings of an object. This was a revolutionary idea because it allowed developers to build massive, complicated systems without everything turning into a tangled mess. All right, let's zoom out now. We've been talking about the individual bricks and rooms, our objects and classes. Now let's look at the overall structure of the entire building, the software architecture. Software architecture is that 30,000-foot view. It doesn't care about the tiny details inside each component. Instead, it's all about defining what the major pieces of the system are and, this is the crucial part, how they're going to communicate with each other. It's the master plan that holds the whole thing together. One of the most common architectural patterns out there is client-server. You use it every single day. Your web browser? That's the client. When you go to a website, your browser sends a request to a server somewhere. That server does its thing. It finds the web page, processes your request, and sends a response back to your browser, which then shows it to you. Simple, powerful, and it's basically the backbone of the entire internet. A more modern version of this idea is called service-oriented architecture, or SOA. With SOA, instead of having one giant server that does everything, you build your application out of lots of smaller, independent services. They're loosely coupled, which is just a fancy way of saying they aren't all tangled up together. This is a huge deal because it means each service can be updated or even replaced on its own without breaking the whole system. It's why a site like Amazon can update its payment system without taking down its product search. So we've gone from a simple idea to a blueprint all the way to a full-blown architecture. But what's the ultimate payoff? Why do we go through all this trouble? Well, it all comes down to building a high-quality product that people actually want to use. You see, good design isn't just about making the software work. It's about how well it works. These things, like being fast, being secure, being easy to maintain, these are the things that separate a great experience from a really frustrating one. And here's the kicker. You can't just sprinkle these on at the end. They have to be designed in from the very beginning. And here is the absolute key distinction that good design helps us get right. Verification asks, did we build the system according to our blueprint? That's building the system right. But validation asks a much deeper question. Does the system we built actually solve the user's real problem? Are we building the right system? The whole point of the design process is to make sure the answer to both of those questions is a huge yes. Which leaves us with a really fascinating question to think about. As AI gets better and better at actually writing the code, the how, what happens to the human's role? Well, the job of being the architect, of truly understanding the user's needs, of making those big picture design decisions, the what and the why, that doesn't go away. In fact, it might just become the most important job of all.